Chapter 2, Section 2.1, Limits and Continuity. In class the last couple days we've been talking about this concept of limit, and if you're looking at the textbook there's a nice little review of some of the ideas we've covered. We started with talking about average and instantaneous speed, which motivated why we need this thing called a limit, and then we talked a little bit more about what a limit means graphically. And now it's time to be really precise about the definition. So this video is actually going to pick up in the second page of your text. Let me jog your memory. We ended class today looking at this table, and we had just talked about how when you solve a limit, when you find this number L, the way you find it is kind of like answering a question that sounds like this. And so from there, the natural question for us as calculus students is, well, how do I answer that question? If that's what the limit means, how do I answer that question in order to answer the limit? In class, we saw a strategy for answering that question based on looking at a bunch of points in your graphing calculator, and a different strategy based on looking at a graph. Now, the next level is to understand that the strategies we talked about today in class, those are strategies for giving you an idea about the limit. And that's different from knowing for sure what the limit is. Think about the difference between saying, I believe the limit is 2, which implies that you could be wrong, but that you're probably not. And then the contrast is saying, I can prove the limit is 2. They're very different statements. Well, this video is going to move down to the level of what can we prove. And you can prove a limit based on its graph or using algebra. When we look at the points in the graphing calculator, you could be really sure, but you're never 100% sure until you've used one of these other two strategies. So that's what I'll show you now. In this lecture, we're going to complete two objectives. First, I'm going to show you how to use algebra to first find the limit and then also to prove that it has to be the right one. And then we will look at what that looks like from a graphic perspective. Your textbook on the second page gives you a formal definition of a limit. This is really important if you go on to higher level calculus, and we're going to play around with it a little bit in class, but I'm not going to waste time in this video explaining it. You should pause the video to copy this down. Please make sure that you copy both the graph and the idea statement, because these ideas end up being what help you apply the definition to new contexts. When we talk about limits and actually solving them, everything starts with these two limits. And the idea behind today's video is that we are going to use these two hard facts to figure out a whole host of other things. The first limit, and this is something you're going to need to memorize, is called the limit of a constant, and here's what it says. The limit as x approaches a of k equals k. In this situation, k is a number, which means if we think about it as a function, it's a constant function, which is a straight horizontal line. F of x equals k is like saying y equals k. In other words, it's a line that looks like this. So understanding what this limit means, we could interpret it as a question, and the question is asking, as x gets closer and closer to a, which is the green line, what happens to y? And the answer is really obvious. Y isn't changing. It's never changing. So as close as x can get to a, the y value is always going to stay k. The second limit that you're definitely going to need to know is called the limit of the identity. The identity function y equals x, or f of x equals x, is the straight line right here with slope 1. And understanding that this has a slope 1 means the closer we get to this a value, whatever it is, if we go up and look for what's happening to y, the y value is always going to be the same as the x value. So we can say that the limit as x approaches a of x equals a. Let's do two examples to make sure that you understand what these definitions mean. Example number 1. What is the limit as x approaches 3 of 7? Well, the first thing I notice is that 7 is a constant number, which means this is a limit of constants. If I follow the rule, that means that the limit at any number here of a constant is going to equal the constant. Make sure that you can keep 3 and 7 straight in this example. Example number 2. The limit as x approaches 3 of x. x is the identity function. So this is a limit of the identity. And the rule for the identity says as x approaches a, the limit of x is going to equal a. And in this case, a is 3. So the limit as x approaches 3 of x equals 3. So you just practiced 3 on your own. If you got them wrong, let me explain very quickly. If you got them right, just confirm that you could explain this to somebody else if they had a question. The limit as x approaches 0 of 2. This is the limit of a constant, and the rule for the limit of a constant is that the answer is the same as the constant. The limit as x approaches 7 of x is a limit of the identity because x is the identity function. The rule for the identity is that the limit as x approaches some number of x equals that number. Finally, I tried to trip you up here. E, as you will remember, is a number. So it turns out that the limit as x approaches pi of e, this is a limit of a constant because it looks like a variable, but e is actually a number. So we're taking the limit of a constant number, and that constant number has to be the answer. So the brilliant thing about these two really simple rules is that we can combine these two rules into a theorem that gives us a lot more information. The first theorem in the textbook looks something like this. And basically, this is using those two rules to make a bunch of more powerful rules. And this is on page 61 of the text if you have it. When you look at a theorem, you always want to look for a premise and a conclusion. And what I would do if I were you is, in your notes really quickly, make a quick table for yourself, something maybe a little bit like this. I would make a chart that says name, rule, and then words. You could put examples out to the side if you want. And you are going to need to know these properties. So there's the name, there's the rule, here are the words describing what it means. I will pause so that you can copy down these rules. But when we come back, we'll talk about a little bit more what they mean. In particular, when you use this theorem, what are you going to check? That's the premise that you need to make sure holds true. And if it holds true, what do you get to do with this information? These are the first 4 of the limit properties. Pause to copy, and then I'll show you the rest. There's number 5. And number 6. So the good news is you don't need to memorize these formulas. You do need to understand what this theorem means. If you're in charge of vocab, don't bother to make these all vocab words, but make one statement that summarizes all of Theorem 1. Here's my stab at summarizing. Basically, what this theorem is saying is if we have 2 different functions and we know what their limits are, L and M, at some particular value C, then we can do a whole bunch of things with the limits. We can take the limit of the sum of the functions, as in if they're added together, we know what the limit's going to be. We can also break them apart using subtraction, multiplication, constant multiplication, and division. I think this will be more real to you if we look at some examples. So here we go. Properties of limits examples. Here's the first one. The limit as x approaches 3 of x plus 7. Well, I know that if I see addition inside of a limit by the sum rule, and I'm going to actually mark that down here, that's what I'm using. By the sum rule, the limit as x approaches 3 of x plus 7 is the same thing as the limit as x approaches 3 of x plus the limit as x approaches 3 of 7. And I just used the sum rule to say, well, the limit of 2 things that are added is the same thing as the limit of the first one plus the limit of the second one. The reason that's helpful is because I know these 2 limits. I know for sure that the limit as x approaches 3 of x is 3, because that's the identity limit. And I know for sure the limit as x approaches 3 of 7 is 7 because that's a constant limit. Now you may in your head say, oh, this looks obvious. This should be a plus right here. That's okay. You're thinking the right thing if this seems obvious. The trick in calculus is to convince yourself that obvious things aren't always true. Think about our first lesson. So only take a step that you can defend. I can defend why I took this step, explaining it by the sum rule. This is sort of a practical application. Sometimes I'll test this same knowledge in a more abstract way. If we know that the limit as x approaches 2 of f of x equals 6, take a moment to make sure you know what's the input, what's the output here. And we also know that the limit as x approaches 2 of g of x is 2. Then what's the limit as x approaches 2 of f of x divided by g of x? So this would be some weird big function. Well, by the quotient rule, I know that this limit right here is the same thing as the limit of f of x as x approaches 2 divided by the limit of g of x as x approaches 2. And that's good news because the limit of f of x as x approaches 2 is 6. The problem told me it was 6. And the limit of g of x as x approaches 2 was 2. The problem told me that. Which means I don't know what g and f are, but I know that the limit of their quotients has to be 3. The two that you just did are pretty much the same. By the product rule, I can split this limit into 2. And I know that the limit of 2 as x approaches 6 is 2, because that's a constant, and the limit of x as x approaches 6 is 6, which means the answer to this limit is 12. Similarly, by the difference rule, if I know the limits of f and g separately, the limit of the whole thing is just going to be the limit of the first minus the limit of the second, which is 7. Again, this probably seems really obvious, and if it does, that's great, because the obvious thing to you is actually our next theorem. And the thing that you probably find really obvious is Theorem 2. Pause the video while you copy this one down. I know there's a bunch of words. When you press play again, I'll explain the idea, and then we'll look at some examples which will help you out. Basically, Theorem 2 is saying what you may have already realized, which is you don't really need to break up each limit into a bunch of other limits. As long as you're working with a polynomial or a rational function, as in something that has exponents or maybe variables on the bottom, but not including square roots or natural logs. As long as we're doing polynomials or rationals, all you have to do to find the limit is really just plug c into the rule for f. Let's take a look at the examples. So by Theorem 2, as long as this is a polynomial, in order to find the answer, all I need to do is plug in 3. Well, good news. This is a polynomial and these are rationals. So the limit is suddenly the easiest thing you'll ever do. When I plug in 3 to all of the x's, I get 3 squared times 2 minus 3. 2 minus 3 is negative 1, times 9 is negative 9, and that's it. You've proved it, you're sure. Same thing down here. 2, everything's defined, so I'm just going to plug in 2 to this rational equation, and I get 2 squared plus 2 times 2 plus 4 over 2 plus 2, which is 4 plus 4 plus 4 is 12, and 12 over 4 is 3, and that's the limit. That's it. That's the answer. Here's the last one. I start out and I see this is a rational function. I'm excited because this seems really easy, and I go to plug in 2, and then suddenly I realize that, if I plug in 2 on the bottom here, I'm going to get a 0 on the bottom. And if you were paying close attention to this theorem, the premise was that both the top and the bottom just the bottom can't equal 0, because the whole thing has to be defined. That's the premise. If you check and plugging this number in would give you an undefined function, you can no longer use the plug-in strategy. We're going to need something else. Well, you might already see what we can do. If I keep the limit for a second and rearrange this function, I could rewrite it to be x minus 4 times x minus 2 over x minus 2. And in this new form, I realize I can cancel these out, which means that this is the same thing as x minus 4, and when I plug in 2, I now get a limit